All right, in this supplement video, we're going to look at another topic that was in AP Calc that they didn't have on the exam. It's another integral application. It's called find the area between two functions. So hopefully you're aware that find the integral of a function gives you the area under the curve. Namely, it's the area under the curve, meaning between the curve and the x-axis, and also between two x values. So basically you have an x value, another x value, and then it sort of gives you this region you can find the area between. Well, integration doesn't just find the area under one curve, it can find the area between two curves. There's going to be two types. One I'm going to call artificial, and the other I'm going to call natural. So I'll look at the artificial version. Basically, in the artificial version, it has to do with picking the x values. In the artificial version, the x values are arbitrarily picked by somebody, so they can be anything. In the natural version, we're going to look at where the curves naturally meet, and they cut off their own area in a, like I said, a natural way. It's just this sort of obvious area sitting there, and we can find it. But either way, I'll show you an example of each. But we're going to look at two functions and see how to find the area between the two functions is the major goal here. And like I said, I'll try to keep it as simple as possible. So the general idea, if you want to do this process, is it's, according to this picture, it's finding this green region. You're going to have, if you're successful, you'll have an upper function and a lower function. Now, it is possible these things cross and do something else, but then don't worry about that now. You can handle it in pieces if that happens. For the section that you want to do this in, or for the easier examples, there'll be a function on top and a function below. So the top function is f of x, the bottom function in this case is g of x, and I want to find this green region. Now, this is what I mean by artificially cutting it off. Somebody just said, I want to find the area from A to B. So there's no reason to really cut it off here, except that's what they want to do. All right. So what you're going to do is determine what the upper function is, what the lower function is, and then you're going to use subtraction, because basically if you just integrated f of x, you would get the area under f of x. So you would get everything from this red line over to this other red line, and from the x-axis up. So if you just did the integral of f of x, you'd get this region. If you want the area of the green, well, you can take away this white region below. Well, that's the integral of g of x. So basically, if you integrate f of x and subtract the integral of g of x, you can find the answer to this. And if you do integral of f minus integral of g, you can just do integral of f minus g. The rule that works that way for addition and subtraction. So after you determine the upper and lower functions, which is important, you need to know which one's on top. But once you know which one's on top, you could subtract the lower function from the upper function. So you're doing upper minus lower. And then you integrate that expression from A to B, and it gives you the area. So what this says is basically the rules. If you want the area between curves, so here's the definition. You need f and g to be continuous on the closed interval AB. And in order for this formula to work the way it says, you need f of x bigger than g of x. If g of x is bigger than f of x, then just reverse their roles. But for this, what I'm writing here, we're going to assume f and g are continuous. They're on the closed interval AB, and f of x is greater than g of x for all of the x's in that interval. All right, so that's all that's saying. If that's true, what's the area between the two curves? You can integrate from A to B of the upper function minus the lower function, dx. Whatever this integral expression is, gives you the area. I mentioned to sketch a picture to help. The reason the picture is helpful is because it just kind of gives you an idea of what's on top, what's on the bottom, and what's the general region looking like. You know, if the region looks like it should have 5 square units, your answer comes out to be 1,000, it helps to kind of have a general idea of what you're looking at. So the picture helps not only for knowing what the top function is, but just for having a rough idea of what, does the answer make sense. For example, for most of these, if you're doing it right, you should be getting positive areas. So if you get a negative number, that can also, not say these can't come out negative, but for now, negative answer can also be a sign that you're not doing things correctly, okay? So once again, to do this, just take one function minus another and integrate it. Now, you can do them by hand, but once again, I'm not trying to torment you here because we're done with the AP exam. So I'm just going to throw these into a calculator. I'm not going to worry about doing the actual calculation on them. I'll assume that if you did your job, you know, oh, I can take the antiderivative and all that stuff. So for these, it's an application. Feel free to use the calculator to get your answer. So basically, it's the setup, just knowing how to set this thing up, which really isn't that bad. You know, it's subtracting two functions, throwing the integral on it. And it doesn't get too much more complicated than this. I'll show you one example. We got to do a little more work, but let's start easy. So the first one says, let's find the area between y equals x plus 6 and y equals x squared. And we want to find the area between 0 and 2. So this is what I mean by artificial. Somebody just gave me the numbers. Someone's like, hey, find the area between 0 and 2, because that's what I feel like having. So it was arbitrarily picked. These are actually easier because we don't have to find the values. Like, these are just given to us. Someone told us them. All right? So let's look at this. I have it on the board in the back, and it's not really that complicated to set up. The big deal for figuring it out is really just figuring out what function's on top of the other. If you know what your functions look like, this actually isn't that much of a challenge, because this is a line, right? It has a slope of 1 and an intercept of 6, and this is a standard parabola that starts at 0, 0 and starts to curve upward. So if I take a look at the picture of this, which I sketched on the left there, the line y equals x plus 6 would have an intercept of 6 and a slope of 1, so it looks something like that. And from that picture, it should be clear that, at least for a while, it's on top of the x squared function, right? Here's x squared, which is the parabola. Now, I just need to see it from 0 to 2. So this parabola does continue onward, but I cut it off just to go, well, here's the 0 and here's the 2. So the parabola is always below the line in here. So the good news is I know what my top function is, and I know what my bottom function is. My top function is the line, x plus 6, and my bottom function is x squared. So according to these rules, the area I'm looking for is the shaded, like, bluish region here. And I can find it by just integrating from my limits, integrate from 0 to 2, the top function minus the bottom function. Now, I put the bottom function in parentheses. In this example, I don't actually have to put parentheses because it's one term. But be careful, if this has multiple terms, you don't want to forget to distribute that negative. So to be proper, I put the parentheses here. Just in case this had more terms, you would want those parentheses. In this case, I don't actually need them, but I'm writing them there just so I remember to talk about it with you. All right? So once I set up top function minus bottom function, integrate it, this thing gives me that shaded region's area. The shaded region's area is 11.3 repeating. Maybe a little more proper for higher math is to give the fractional answer. It's 34 thirds, or 11 and 1/3. All right? So, and once again, does that kind of make sense? I mean, that seems like it's not some unusual area. If my answer came out as 1,000,000, I'd be like, oh, well, that's not 1,000,000 square units. But, you know, it seems reasonable that that's 11 1/3 square units. All right? So this is calculating the area between curves. This is the arbitrary version. So someone just said go from 0 to 2, and I did. I'm going to do the same example, but I'm going to do it from the perspective of the natural area it encloses. So I'm going to look at this example one more time, but we'll look at it from a different perspective of what if someone doesn't give us the 0 and the 2, and they want us to just kind of naturally see what the functions do. All right, so let's look at that example, or we'll talk about it first, and then we'll get to the actual example. So let's look at what's called enclosed area, or a naturally enclosed area. So what this says is some functions actually meet naturally and enclose an area between them. So in this picture I showed, I found this online, y equals x, and the parabola 5x minus x squared. Now, these two functions actually naturally enclose an area. So if someone doesn't actually give you the limits, it may be because there's these natural pinch points and there's this area that's naturally in between the curves. So in this case, the parabola is the top function, the line is the bottom function. The problem is you would have to find these intersection points. There's two ways to do it, so I mentioned over here. In order to do the natural area, they'll give you the two curves, but they won't give you the x values because they'll go, oh, well, hey, find the area that they naturally enclose, and then you'll be able to find that by find the intersection of the two functions. You can do that manually by setting them equal. You can also do it on the calculator, and I'll show you both. So find the intersection of the two functions by setting them equal. So if I set 5x minus x squared equal to x, set them equal to each other and solved, I'd get a quadratic and I could find the values. I'd actually get two values. And the values should be 0 and 4. Once you find those x values, use those x values as your integration limits, right? So this is basically the same as before. It's just they make you find these x values because there's a natural way of getting them. So I'm going to look at the same example instead of them artificially making one, because like they could do that for this too. They could say find the area between 1 and 2 and artificially cut a slice. But if they don't tell you that, they want this natural area where these things sort of pinch each other off and create this green area. Let's look at that same example we just did. It says find the area enclosed between y equals x squared and y equals x plus 6. But notice they didn't give me any limits. So if they're not giving limits, they want the enclosed area, the naturally enclosed area. Or they could say that or show it in a picture or something. So this is a little more advanced. I'll show you it manually, and then we'll look at how to do it in the calculator because the more advanced functions could just be, that they could be hard to solve. So you can use technology to be able to get them. So let's look at this example again, but we'll look at the naturally enclosed area. So I did everything manually over here. Like I said, I'll show you the calculator in the end. These are the two functions, x squared, x plus 6. I already drew them. You already saw that it was a line and a parabola. But remember that if that parabola were to keep going on either side, it would have these natural meeting spots and cut off this natural area that I shaded in red. So how will we find those? Well, if you want to do it, if you feel like it's easy enough and you want to do it manually, you can just set these equal to each other. So where are these two functions equal? That will give you the intersection points. Well, where these two functions are equal, set them equal and solve for the x values that make their y values equal, right? So solve this. This is a quadratic, so it's not bad to solve. You set equal to 0 and factor, and you get that these two functions are equal to each other, aka they intersect at x equals 3 and x equals negative 2. And that makes sense from the picture. If you were to draw them, you would see this is where they intersect. So these are your limits of integration because they want the naturally enclosed area. So now that you found the x values that enclose them, you want to integrate from negative 2 across to 3 and figure out what this area is. So it's the same setup. That's still the top function. That's still the bottom function. But now I'm integrating from negative 2 to 3. And I get the answer 20.83 repeating, which a little more precisely is 125 over 6. All right. So lastly, because that's pretty much all there is to it, the only thing that can really make this process kind of difficult is, well, there are some more things that make it difficult, but for this lesson, the only thing that would really make this a little more difficult is finding these intersection points. So if you don't think you could do them manually, or you don't feel like doing them manually, you can get them in the calculator. There's a command. So let me enter these functions in. So I'm going to enter in x squared and x plus 6. And if we take a look at the graph, and I have to change my window here because my window's, for some reason, strangely proportioned here. So let me, all right. Standard, there's that. All right. Finally. All right, so there's the two functions. You can see that there's those natural pinch points there, right? That there's those two spots where the line's meeting the parabola. If you want to find them, one way is if they're obvious, if they're integers like they are in this case, you could go to the table and just look for where they're equal, right? That's if you suspect they're really easy values. You could just scroll through here. Now, we know negative 2 is one of them. So if you look at negative 2, you see they're both 4. And we know the other one's 3. So if it's a really simple function, you might be able to just find them by doing this. But this isn't a reliable method, especially if they're decimals. So a little more advanced way to get it, if you suspect that they're decimals and you're not quite sure what they are, is you can use the intersect function. So what you do is you go to second, you hit second and trace. That's the, it's hard to, wish I had more hands here. Hit second and trace. That puts you into the calc menu. And in the calc menu, you can calculate and intersect it there where it intersects, right? Intersect is where the two functions meet. So you can do that by hitting number 5. So it's going to ask you to select the two curves. Now, I only have two functions on here. The reason it asks is because I could graph like 7 functions and it would make me pick the two that I wanted. If you only have 2 in there, you can just hit enter and enter. It selected the two curves, and then you provided a guess. So then you move along with your cursor and you go to where you think the intersection point is, and you hit enter, and the calculator. Sometimes it's slightly off, so realize if you get like 3.9999999 or something like that, it really is 4. But most of the time it'll hit it right on. So notice that the intersection point is -2, 4. Now I don't really care about the y value, but I care about the x value. That x value is -2. If I want to do it again, let's see if I can do this with one hand. I can get the other one by going through the motions here and going to the other side. So I hit intersect, so I went to second trace, that 4th button up top. I'm going to hit enter and enter on the two curves. And then I'm going to scroll over to the other intersection point. And as long as you're close, it should nail it. It's 3 and 9. So if you don't want to go and solve it manually, or you can't solve it manually because the functions are really strange, you could imagine like a trig equaling a e to the x or something weird like that, the calculator will at least give you decimals, or if they are integers that you could have found, they'll give you the integers. So that's how you can do it in the calculator. So I said, if this part's not going to be too bad, if this is a little more challenging, just get a calculator to do it for you. Now, in the next video, we'll talk about these can get a bit more complicated than what I'm showing you. For example, the function can cross itself a few times. You can also get functions where that you have to break it into sections. So I'll leave that for another time because I said I think this is, we're getting near 20 minutes here, so this is more than long enough. So the assignment will have one that has the area defined, like I said, the arbitrarily picked one, where someone just picked 2 numbers, so you can just set up that integral. The second one will be the naturally enclosed area, which will require you to do either saying it equal, but I think the one I have, saying it equal, is a little difficult, so it's easier to just get the intersection points in a calculator. Okay, that is, or you can look at the table like I showed you. Okay, so that's find the area between 2 curves. Basically use the subtraction formula in the integral, and you should be fine. And let the calculator do most of the work for you. That way you don't have to calculate antiderivatives. All right, that will end this video. So that's your lesson for the week. Till next time.